Hello guys, welcome back to a new video discussion in plane stresses. Now, in my previous video, we discussed about the transformation of normal stress and shear stress, okay? And we computed the equivalent normal and shear stress in the inclined plane of our stress element. And the only method that we adopted or we utilized in determining these transformed stresses is by using the very long, which is the transformed equation. But in this video, we will be solving it using different approach. We have what we call Mohr's circle. Okay, now in Mohr's circle, we just need to plot our shear stress and normal stress in our stress element in our Cartesian plane, in which this Cartesian plane here, our y-axis, this is the shear stress, and our x-axis here, this is our normal stress. Now, what is a Mohr circle? Now, a Mohr circle, the coordinates of each point on the circle represent the normal and shear stress that act on a specific plane that passes through the selected point in the body. So, all the points that comprise the circle, so all the points in the circumference are the coordinates of the normal and shear stress that act on a specific plane. Okay? So therefore, if this point here, this represent the normal stress at y-axis and the shear stress xy. So at this point, during this plane, so this line here represents the plane during we have these stresses. Okay, now looking back to our stress element, so we have the stress element here. This is the original state of stress. So this is the coordinate, okay, of this y phase of our stress element, in which our x coordinate here, that is our stress y, and the shear stress xy. So this is also different coordinate. Okay, so all you need to do is to plot this coordinate and this coordinate here, then you connect like this one. So we plot here the normal stress y and the shear stress xy. So these coordinates here represent the stress and the shear stress during the original state of stress of our stress element. Okay, and this one here, this also the coordinate for the, let's say this, since this is x, so we have the normal stress x and the shear stress xy of our original state of stress element. So again, all the point in our Mohr circle represents the normal and the shear stress at any plane. So this one represents the plane. Okay, now how are we going to plot this normal and shear stress in our Mohr circle? Now we have a convention, sign convention here. So if you have shear stress that has a clockwise moment about the center of the element, it should be plotted above the normal stress axis. So this one here, this is the shear stress, since this is plotted above the normal stress axis, so therefore the rotation of that shear stress is clockwise. So therefore, if this is the center of our stress element, so the direction is that way. Okay, since the rotation of our shear stress is clockwise. Okay, if it is clockwise, then that is positive in our Mohr circle. So it might be confusing for you, since we have different sign convention when we use the transformation equation. Okay, so remember this sign convention. If you have clockwise rotation of the shear stress, that should be plotted above the normal axis, or that is the positive coordinate. Okay, so if you have counterclockwise shear stress like this one here, so this is rotating counterclockwise, so therefore this shear stress here should be plotted below the normal stress axis, so like this one here. So this is rotating counterclockwise with respect to the center of our stress element. Now, for normal stress, if we have tension or tensile stress, then that should be positive. So therefore, if this our origin, if we have a normal stress positive or tensile stress, then that should be plotted on the positive axis, so in the right side of our plane or Cartesian plane. Now, if we have compressive stress, okay, then that should be negative normal stress, so that is in the left side of our origin, left side of our plane, Cartesian plane. Okay, so those are the sign conventions that we need to remember when plotting Mohr circle. Okay, now we have, since again in our stress element we are required to determine the inclined plane. In this inclined plane we have angle theta. Okay, now the rotation of our angle or the plane now should be twice the rotation in this Mohr circle. Like for example, if we have theta at this point, so therefore since the rotation is counterclockwise, so therefore we need to rotate counterclockwise from this original state of stress plane. So we rotate counterclockwise, and the rotation should be twice the angle of transformation, that is 2 theta. So this is now our new plane, and this coordinate here, and this the shear stress and the normal stress at this point, that is our transformed, okay, at the same as at this point here. The normal stress and the shear stress here are our transformed stresses at angle theta rotating counterclockwise. Okay, so the same as with the rotation of our angle would be the same with the rotation in our stress element. The only difference here from using the transformation equation is that when we have counterclockwise rotation in our shear stress, that should be plotted below the normal axis, and if we have clockwise rotation of our shear stress with respect to our center of stress element, then that should be plotted above the normal stress axis. Okay, now let's try to compute problem. Now we have our new example here, the same as with the problem from the first part of this video. We have the stresses shown act at a point on the free surface of a stressed body. Determine the normal stress and the shear stress that act on the indicated plane surface. So we are going to determine the normal and the shear stress at this inclined surface here. Okay? So again, if we rotate our stress element, this would become like this one, in which we have a rotation of 40 degrees. So therefore, we have rotation of 40 degrees counterclockwise. So at that point, so 40 degrees. Okay? Now, the shear stress and the normal stress at this inclined surface is just the transformed normal and the shear stress of this shear and normal here. Okay? So since this is sigma y, so therefore when our normal stress on the incline is, we have the transform of sigma y, that is the sigma y prime. Okay, and let's assume that it is compression. Now the transform of the shear stress is, we have, let's assume that it acts this way. We have the shear stress x prime y prime. Okay, so we are going to determine the transform of sigma y and the transform of our shear stress. But first, we need to plot these stresses here in our normal shear plane, in which the vertical is the shear stress and the horizontal is the normal stress. Now we have the first pair, 38.5 and 66 MPa. Now we know that our normal here is compression, so therefore this is negative. And then the rotation of our shear stress, which is 66 MPa, rotation is counterclockwise, so therefore we need to plot that below our normal stress axis, so below the normal stress, so at negative shear stress. So this is negative also. Now we have at the X face, we have 16.5 MPa, which we know that is positive since that is tensile, and our shear stress here, which is the rotation, is clockwise, so therefore we plot that above our normal stress plane. So we set that as positive, okay, since the rotation is clockwise. So let's plot. We have the first coordinate 38.5 and 66, that's negative, so therefore we have at this point, let's say this is negative 38.5 and negative 66, so we have to go downward, that is 66 here. So let's say this is negative 38.5 and negative 66 shear. Now for this one, 16.5 and positive 66 MPa, both are positive, so we go at this side here. So let's say that's 16.5 here, and we have positive 66 MPa upward. Let's assume at this point. So we have the coordinate here, which is 16.5 and negative 66 shear. Okay, it is just the same as plotting a Cartesian plane or an X and Y coordinate. And then we connect these 2 points. We have this one, and then we draw a circle, this one. Okay, so we have to locate the center of our circle. So the center is at this point, let's say at this point. Now we just need to get the average of our normal stress to determine the coordinate of our center. Let's say that's X. So we have X is equal to, which is 16.5, then minus 38.5 over 2, then we have the center, which is at negative 11. Okay, so we have the location of our center at negative 11. And then after that, we compute for the radius. Okay, now the radius is this one. Since we know that this height here is equal to 66, okay, and this length is equal to, now we know that is 38.5, okay, this one, and we have the length here, which is 11, so we can compute this length here, which is 38.5 minus 11. We have the length 27.5. Okay, that is 38.5 minus the location of the center, that is 11. So we can now compute the radius. Our radius here is just Pythagorean theorem. We have the square root of 66 squared plus 27.5 squared. We have r is equal to, we have here 71.5. Now we can compute the angle, let's say this alpha. So we have our alpha here. Tangent of alpha is equal to 66 over 27.5. Then we have 67.380 degrees. We have here 67.380. Now take note, there is a counterclockwise rotation of our stress element, which is 40 degrees counterclockwise. Then we have to rotate our Mohr circle or our plane here into twice this angle. We have 80 degrees counterclockwise. So we have from this original plane, we rotate 80 degrees. So we have this rotation 80 degrees. Let's say at this point, so we have 40 times 2, that is 80. Okay, now this is our new inclined plane. Okay, now take note, the 16.566 here transformed into the coordinate, this one here. So it became, or it transformed to this point. Now 16.5, this is sigma x, so therefore this would become here sigma x prime. Okay, and our shear here is shear x prime y prime. Whereas this stress here, we know that 38.5 is sigma y. Due to rotation, it moves from this point to this point here. Okay, so there is a transformation of the stress, and this would become here sigma y prime. Okay, and our shear stress, which is shear x prime y prime. Now, since in our stress element, in this surface, we have the stress normal and shear, which is the transformation of our sigma y. Okay, so sigma y prime. So therefore, in our Mohr circle, we will be determining sigma y prime, okay, instead of sigma x prime. So we will be determining the stress at this point here, or the coordinate at this point. Okay, now we have the radius, which is, we know, 71.5. so all we need to do here is to compute this height here, which is this, that is our shear, and from this origin to this point, that is our normal stress y prime. Okay, that is the coordinate at this point. So in order to compute these stresses, we need to compute first the angle here. Let's say it's angle beta. Okay, now angle beta here can be computed by knowing that this angle beta here is equal to the angle at this point. It's beta, in which we know that this beta here can be computed by just beta is equal to 180 degrees minus 80 degrees, okay, minus the angle at this point, which is 67.380 degrees. So we have our angle beta here, which is equal to 32.62 degrees. Now we have the angle of beta here, which is also 32.62 degrees, since they are equal. So we can isolate this triangle. We know that this height here is the shear stress, okay, and then our length here from the center to this point, since we know that this one is 11, okay, that's 11, then this length here from the origin to this point is sigma y prime. So we could say that the total length from the center to this point is 11 plus the sigma y prime. Okay, and this angle here is 32.62. Now we have the radius, which is 71.5. So we can now compute for the shear stress by using sine. We have sine of 32.62 is equal to the opposite over the hypotenuse, 71.5. Then we have our shear stress here, which is equal to 38.543, which is in mega pascal. So this is the shear stress x prime y prime. So this is equivalent to shear stress x prime y prime, or the transformed shear stress. Now for the sigma y prime, or the transformed normal stress, we can use cosine. Cosine of 32.62 is equal to the adjacent 11 plus the sigma y prime over the hypotenuse 71.5. Then we have our sigma y prime here, which is equal to 49.222 megapascal, and this is in positive, so therefore this one is tension. Okay, so this is the transformed normal stress, or the normal stress and the shear stress on this inclined plane here. Now if you want to compute for the transformation of our sigma x here, or the sigma x prime, then you just need to compute the coordinate at this point. Okay, now we have the same answer when we use the transformation equation during the part 1 of this video and using the Mohr circle. Okay, so it's up to you on which you would think is the easiest method. Okay, but when you use Mohr circle, you do not need to memorize those transformations. So I would suggest you practice these two approaches. Now, if we try to plot this shear and normal stress in our stress element, we would have, now we know that we are looking for the stress and shear at this inclined, which is 40 degrees. Okay, now we have observed that our normal stress here is in tension, so therefore it is acting away on the surface or on the face of our stress element. So we have our normal stress here, which is in tension, this one. So we have 49.22 or 222 megapascal. We have 49.222 megapascal. Now for our shear stress, now we know on our Mohr circle, our shear stress is located below the normal stress axis. So therefore, our shear stress here has a rotation which is counterclockwise. Again, if we have a shear stress rotation which is counterclockwise, then we have to plot that below the normal axis. If it is clockwise, then we have to plot our shear stress above the normal stress axis. But in this case, our shear stress is below the normal stress axis, then the rotation is counterclockwise. So we have our shear stress direction, which is this one. Okay, the rotation is counterclockwise. So we have here 38.543 megapascal. On the opposite side, we have tensile as well, 49.222, and then in the opposite direction of our shear stress, we have 38.543. So this would be our stress element. Of course, we still have here unknown. Let's say that is our sigma x prime. Okay, and we have our shear stress, which is also, of course, equal in magnitude 38.543. In the opposite direction, we assume that it is compression again, sigma x prime, and we have the shear stress 38.543. So I'll leave that to you. You compute for the sigma x prime and you try to plot this in our stress element with its correct orientation. Okay, so this is our possible stress element. So that ends our example number 2. Okay, where we have computed our shear and normal stress in our inclined plane. So we have computed the normal and shear stress on this plane. Okay, and that's it for our problem number 2. So thank you for listening.